Hello everyone, my name is Daifung Liam, and this is my final project presentation for the course CSCI S89 Deep Learning at Harvard Extension School, Harvard Summer School, Harvard University for the Master of Data Science. So my project focuses on the application of state-of-the-art deep learning architectures to the problem of semantic segmentation in both satellite and UAV imagery. In my presentation, I will cover my motivation, the technologies used, the experiments conducted, and the key findings from the project. My initial interest in this topic came from a related medical imaging project in the course CSCI E25, where I used UNet and DeepLab v3 Plus to segment brain tumors. I realized that many techniques in medical imaging can be repurposed for geospatial analysis, whereas semantic segmentation plays a critical role in land cover classification, disaster monitoring, and environmental analysis, as well as defense industry. My project allows me to extend my deep learning knowledge into a different but equally impactful real-world domain. For the dataset, I use a custom augmented satellite and UAV image dataset. Each image is 256 by 256 pixels with RGB channels, and the masks are indexed from 0 to 7, which I narrowed down, representing 8 land cover classes. I apply data augmentation such as flipping, rotating, cropping, and scaling to increase the diversity of the training data from the 3 data sources that I have, including 2 from the satellites and 1 from the UAV. This technique was covered in one of the lectures, and I find it crucial for improving model generalization and mitigating overfitting. So for the technologies, I use Keras with TensorFlow backend, train models on Google Colab Pro Plus with an A100 GPU, and trained each model for up to 100 epochs. Evaluation metrics include pixel accuracy, mean IOU, classification reports, and confusion matrices. My project applies 3 major architectures in semantic segmentation: UNet, DeepLab v3 Plus, and PSPNet. Each model is tested with and without regularization techniques like L2, penalty, top out, and early stopping. UNet is a symmetrical encoder-decoder architecture introduced for biomedical image segmentation. The encoder captures context via convolutions and pooling, while the decoder restores resolution using transposed convolutions. Then skip connections pass spatial information directly from encoder to decoder, improving localization. I find it highly efficient and it performs well on small dataset and the augmented dataset. DeepLab v3 Plus extends DeepLab v3 by adding a decoder module to refine boundaries. It uses a child's or dilated convolutions to expand the receptive field without increasing parameters, and then incorporates a child's spatial pyramid pooling, which is ASPP, to capture multi-scale context. This is a strong performer in segmentation tasks, balancing accuracy and efficiency. PSPNet introduces the Pyramid Pooling Module, PPM, which pulls features at multiple spatial scales to understand global context. While it offers deep contextual insight, it's computationally expensive. I implemented both a baseline and a regularized version using top-out and L2 weight decay. I trained each of the 6 models, UNet version 5, version 6, GitLab v3 Plus version 4, version 5, PSP.NET version 1, version 2 on the same dataset using the same augmentation, same learning rate, same optimizer, and same loss function. Validation performance was evaluated on 20% of the data using accuracy, IOU, F1, precision, recall, and visual inspection of segmentation quality. Talking about the model comparison, UNet version 5 had the best accuracy, where the IOU trade-off with the minimal overfitting. Meanwhile, the DeepLab v3 Plus version 5 showed the strongest generalization with high IOU but longer training time. PSP.NET models underperformed despite having the most parameters. Metrics like training or validation accuracy, IOU, and losses were plotted over 100 epochs. So I extracted the best epoch based on validation IOU and used those metrics for the final evaluation. The DeepLab v3 Plus version 5 and UNet version 5 peaked early and remained stable, while PSP.NET models struggled to improve even after many epochs, suggesting architectural inefficiency and data incompatibility. The classification reports revealed that UNet version 5 and DeepLab version 3 plus version 5 had high precision and recall across most classes, especially for dominant ones like vegetation and roads. Meanwhile, the minority classes like rivers and rooftops had lower scores. PSP.NET models perform inconsistently across all classes. This reinforces that model architecture and regularization play crucial roles in class-specific accuracy. Here are my qualitative results showing predictions from all 6 models alongside ground truths. UNet version 5 produced clean segmentation with well-defined boundaries. The DeepLab v3 plus version 5 also performed well, though it missed small objects. The PSP.NET models produced non-zero outputs, struggling with spatial detail. So here's my ranking. UNet version 5 is the best overall visual quality. Its prediction is almost indistinguishable from ground truth. It captures row outlines, circular building clusters, and class transition with sharp and smooth boundaries. High pixel level correspondence and minimal noise are also observed. There's the impressive performance with relatively simple architecture and the dropout. Besides, UNet version 6, which is similar to version 5 but slightly less precise. It was added with L2, which stabilizes training, but result shows minor smoothing of edges compared to version 5. The boundaries are still scripts, but some fine details are blurred. But still, it ranks very high among all 6 models. DeepLab version 3 plus version 4, this is a balance between accuracy and complexity. There's very good detail on vegetation belts and building outlines. There's also slight softness in detecting narrow roads, possibly due to deeper features being upsampled. The ASBP module enhances context awareness, and edges are moderately sharp. The DeepLab v3 Plus version 5 is a combination of dropout and L2, so there are less clear boundaries here. It was added with regularization, which prevents overfitting, but in fact, it sacrifices some boundary clarity. The predictions look slightly fuzzier, especially in smaller object clusters. So there is a trade-off observed. Better generalization, lower overconfidence, but visual alignment drops a bit. The PSPNet version 2 ranked 5th because of over-smoothing effect visible. There is coarse segmentation with weaker detail separation. The route buildings blend together. Road lines become thicker blocks. They are likely due to over-regularization or excessive pooling plus a dropout. The PSPNet version 1 shows the lowest visual alignment. Row and building segmentation is noisy and patchy. Large errors misclassify and blurry. The model likely suffer from underfitting or ineffective upsampling. Its edges are the least sharp. Prediction seems visually detached from the true layout. So, to summarize, the ranking based on the visual results between ground truth and prediction would bring up to a ranking on my own. So I would say that the UNet version 5 would rank first, thanks to the best balance of detail and clarity. The UNet version 6 would rank second because of slightly softer performance than version 5. Meanwhile, the DeepLab version V3 Plus version 4 would rank third, thanks to the strong semantics understanding. The DeepLab V3 Plus version 5 is considered moderate because of its slight degradation due to regularization. The PSPNet version 2 is considered weak, in my opinion, because they are over-smoothing and coarse structures. Unfortunately, the PSPNet version 1 is considered poor because the predicted images are blurry. The model fails to capture key patterns. So my ranking based on performance, efficiency, and generalization is as follows. In short, UNet version 5 was the best lightweight model. DeepLab V3 Plus version 5 had the best balance overall, and the PSPNet models did not scale well despite their complexity. Here are some key takeaways. My project taught me the importance of model architecture choice, how regularization affects learning stability, and the trade-offs between performance and computational resources. Data augmentation proved critical for robust performance. Visual inspection is as important as metrics in segmentation tasks. Some concepts that I apply are from nearly every lecture, including weight initialization and optimization, CNNs and pooling, regularization and dropout, data augmentation, loss functions, and evaluation matrix. Therefore, my project synthesized theory and implementation effectively. My project demonstrates how deep learning can be leveraged to perform pixel-accurate classification on satellite and UAV imagery. UNet and DeepLab V3 Plus models are well suited for this task, each excelling under different constraints. This experience deepened my understanding of real-world application of deep learning. That is all of my presentation. Thank you for your attention and interest in my research and presentation of CSCI S89 Deep Learning at Harvard Extension School, Harvard Summer School, Harvard University of the Master Data Science. Thank you.